Alright guys, so in this video we're going to continue our focus as thinking as volume as an integral. Alright, if you remember from the beginning of this lesson, our goals were to do just that, to really understand volume and integrals and the relationship that they play with each other, specifically thinking about cross sections and the areas of those cross sections. And we said that we wanted to go ahead and find a method for slicing and creating a volume, right? And so we thought about the solid, and then we thought about what would be a typical cross section. And then you tried finding a formula that fit that cross section, whether it was x squared for a square, maybe it's pi r squared for a circle, or whatever the case may be. And then you want to find the limit of integration from blank to blank of how big this figure is, or how much of the figure, the solid of revolution, is going to be. And then we can actually take the integration to find its volume. And so today we're going to look into another example in which we talk about a washer as a cross section, where there's a hole in that cross section. And so what you see on the screen right now is 3 different images. And there are 3 different images that have broken up this example in a couple different ways. And let's look at the example here. Okay? So the example that we're looking at, all right, it says there are a region in the first quadrant enclosed by the y-axis, the graphs y equals cosine of x, and y equals sine x. It's going to revolve all that around the x-axis, forming the solid that we see here. Find the volume. So let's think about this for a sec. All of this information, all these curves have now created a solid of revolution by rotating around the x-axis. And as you can see on the inside, this cone that you kind of see right here, as I'm kind of outlining in this case, this cone right here is what's kind of empty, right? This is the empty part of it. And so if I slice it through, I end up having this hole in the middle. And the hole will change as I get farther down the x-axis, all right? And so you want to kind of think in this example, this is the face of the cross section that we are seeing, that I'm outlining right now. And then even further, what we've done in this image is we've now kind of looked at it as a 2-dimensional figure, as if this was kind of going into that cone, and this is kind of that part that is being sliced, sliced, and sliced. All right. So let's continue to look into this. So where do we go from here? Okay. Well, we got to think to ourselves is, one, first and foremost, where are we actually going to be looking from this material? All right. Well, each cross section, all right, perpendicular to the actual axis of revolution, which we said was going to be the x-axis here, forms that washer-looking shape, right? It's that circular focus, that circular region with another circular region cut out from it. So remember, we want to find that area of that washer and take it all the way from point A onto point B. So where can we find this actual area of the washer? Well, think about it. Think about what this is. This is the area of the shaded region, which is the area of the whole circle minus the area of the cut out part from our washer. So really, it's the area of the whole circle pi r squared of our farther radius, which is going to be our farther function, minus the area of pi r squared, which is to the closer function, or the lesser function that we are dealing with. Okay? So where are we going to find each of these particular ones here. Well, what's the radius actually going to look like? Well, in our example here, the cosine graph is going to be the upper graph. It's going to be above here. Because, right, let's look at maybe this one. This probably easier right here. Because the cosine starts here at 1. Sine starts here at 0. So that's how I know that our cosine graph is going to be above our sine graph. So the big R for radius is the radius from the circle to the cosine graph. The little r is that radius from the center to our sine graph in here. So now let's take a look at how we can kind of actually represent this in some mathematical terms. So let's think about this for a sec. Area of a circle, pi r squared, right? The area of a circle is pi r squared. So if that's the case for the area being pi r squared, in this particular washer that we're dealing with, it would be technically the area would equal pi times big R squared minus pi times little r squared. Well, what does that look like for us? Well, that means the volume in this case will be the integral, all right? And so now where are we going? From what to what? Well, we need to kind of think about where that intersection is. Well, think about what happens here. Where's that first intersection where cosine and sine meet up? Well, hopefully we remember back from our trig days, that's going to be at pi fourths. So this is from 0 to pi over 4. And if you wanted to throw that into a calculator and find that intersection because you didn't quite, recognize that, then by all means, go ahead. All right. And so now we want to take our radius, which is the cosine squared function, minus the sine squared function. So really this is going to be pi times cosine squared x minus pi times sine squared x dx. Okay? All right. So now let's think about this for a sec. For me personally, I'm starting to notice that there's pi in both of them. So let's start thinking about possibly making our lives a little bit easier and seeing if factoring out a pi will actually be a little bit more beneficial for us. So I want to go ahead and take out this pi, right? Because think about what's going to possibly happen in here. We can have any possible nice little identities or anything kind of coming on in to play. Well, think about some trig identities that we have in there, okay? So right off the bat, I want to bring this pi on the outside. And cosine squared x minus sine squared of x. That brings us back to our trig identities, because it is true that cosine squared x minus sine squared x is equal to cosine of 2x here. Well, this is a heck of a lot easier to integrate at cosine of 2x. This will equal pi times, well, cosine 2x, take out our 1/2, so we have times 1/2 sine of 2x. So pi multiplied by the evaluation from 0 to pi over 4. And just to kind of make our lives a little bit easier and simpler, we can see that this comes on out to be pi over 2 units cubed. All right. All right, guys, so an interesting problem that we see in there. So we're going to have a few of these examples as we get into our practice lesson when we get back from this video. So we'll have some practice ones that go along in there. My challenge to you on this one is to regraph this on your own and really see where this solid of revolution is coming from. So regraph these, see as your own, and see if you can come up with almost your own pictures of these graphs like we did and we blew up for you here. And we're on to the next one.